All right, today's lecture is going to be on net ionic equations, but instead of forming a solid, a precipitation reaction, we are now going to do the second type of net ionic equations that I want you guys to be aware of, and that type is called an acid-base reaction. So when we mix an acid and a base, they neutralize each other. And our last unit that we'll get to in May is going to be on acid-base chemistry. In specific, we'll talk a little bit of something called the pH scale. Acids have very low pHs, bases have very high. Neutral solutions like pure water, distilled water, a neutral pH is right at the 7 mark. So when we mix an acid and base, they nullify, they neutralize each other, forming a substance that is closer and closer to a pH of 7 or neutral. Okay? Now, first of all, before we get into the net equations, you have to understand a little bit about acids and bases. I'm not going to go into too much depth yet because, again, the next unit will mainly cover that, but I want you to at least have a little background knowledge to get your idea and understand some of these concepts. So an acid, as you can see by definition, an acid is a substance that donates a proton. A proton is an H+. It's a hydrogen ion. And if you remember back from hydrogen, hydrogen is the simplest element. It contains a proton and an electron. Well, an H+ particle has the electron removed. So all an H+ ion is literally a proton. There's not even a neutron. It's a proton. So acids donate protons. So if I put an acid into water, the acid will give H2O a proton, an H+, and that is going to cause water to become H3O+. And we call this particle the hydronium ion. The more and more hydronium ion you have in water, the more and more acidic the solution becomes. So a high concentration of hydronium ions tells us you have a very acidic solution. Bases, on the other hand, water is a very interesting molecule. Water can accept a proton, but also hydrogen can donate a proton. So water, when you put a base into water, it pulls a proton off of water, accepting it, taking it, and making it part of its formula, but then it converts H2O to OH-. And OH- is the hydroxide ion, and the hydroxide ion determines how basic a solution is. So a solution that's very basic has a high amount of hydroxide ions. So these are the two key ions we're going to see in some of these reactions take place, which is the hydronium ion and the hydroxide ion. Okay. In general, if I mix an acid with a base, what's going to happen is they're going to neutralize each other, forming water, because the acid will give the H+ to the base, and because the base typically contains a hydroxide ion in its formula, hydroxide ions and a proton together, when that acid donates that proton to the hydroxide, the base, we form neutral water. So this is how they neutralize each other. So the acid and base will always form water. That's going to always be one of the products of all these net ionic equations for today. And the second substance is usually the salt. The salt is a ionic compound, which is usually the combination of the cation of the base with the anion of the acid. So it's the front part of the base with the negative part of the acid. They come together, and that forms a salt. Now, most often these salts are soluble, but again, you can check your solubility table from our last exercise on your Chem Helper to really guarantee if that salt is soluble or not. Most often it will be. Okay? So therefore, not only will it form a salt, but it will be in its dissociated form. It will be separated. Okay? One last thing we want to talk to before we get into the actual acid-base reactions is this concept of a strong acid versus a weak. Now, when you see the word strong or weak, you are going to think that, oh, that acid, there's a higher concentration of acid versus one that's weaker. That's not the case. A strong acid is one that completely dissociates in water. So therefore, one of the classic examples of a strong acid is HCl. We've often used HCl in a lot of our labs that we did this year. HCl is a strong acid, which means when I look at it at the particular level, so I have a picture here of a beaker and a little scoop of that solution. If I were to blow it up and look at its at atomic level, what would we see with an electron microscope? Well, we would see none of the solution would contain HCl, because HCl, when we put it into water, it immediately donates all of its protons to water, forming hydronium ions and chloride ions. The HCl, when you put it in water, is going to give its proton to water, producing hydronium ions. And because an H plus is removed from HCl, what do we have left over but the chloride ion? So what you would see in a strong acid is you would see none of it would be written as HCl. If you were to draw particles of HCl in this window, you would be incorrect, because HCl is a strong acid. So I've got to erase those here. What I would see in this picture instead would be a bunch of hydronium ions floating around and a bunch of chloride ions. And you'd have to have equal amounts of each, because you'd have one of each. Each HCl would produce a hydronium particle and a chloride ion, and therefore the particles are still canceled out neutrally. There's a positive and negative, but all of the acid would be separated into its ion form. It's completely dissociated, much like a soluble ionic salt, where it completely dissociates into a cation and anion. So strong acids completely dissociate into hydronium particles and negative ions. Okay? Weak acids, on the end, very little of it dissociates. So instead of having a single-sided arrow, my AP students will often see the National or College Board put a double-sided arrow. That double-sided arrow means that just a small amount of that acid will dissociate. A little bit of it will dissociate, producing hydronium. In this case, we have acetic acid, which is good old vinegar. So we'd have the acetate ion, the negative part of the acid, and the proton, again, would be given to water, forming hydronium ions. But only a small amount of it will do this. So in my picture, if I were to blow it up, maybe I would see one of its particles would be dissociated, but almost all of it would actually stay together in its molecular form. Okay, we would have almost all of it would stay together as acetic acid. Very little of it would separate into its hydronium ions and its acetate ions. So that's what it means to be a weak acid. It doesn't necessarily mean that the concentration is either stronger or weaker. What it means is how much of the acid has been broken apart into its hydronium ions and how much of it is still intact as its molecular structure. Now, if I were to add a base, the base would either, if I were to add a base to this acetic acid solution, the base would go and attack the hydronium ions, because the hydronium ions would donate the proton to the base, forming water. If I put a base in a weak acid, instead of attacking the H3O+, because there would be so little of it present, the base would most often attack the acetic acid, because the acetic acid still will donate the H+ to the base. So it depends on who's going to donate the proton. But if I have acid present, no matter if it's weak or strong, there will still be a donation of a proton to the base. And it'll either come from the H3O+, or it'll come from the acid itself, depending upon if it's a weak acid or a strong acid. So this is probably the most difficult concept for you guys to kind of understand. I'm not really going to test you on it. I just want to introduce you to this concept, and then we'll talk more about it in depth when we get into the acid-base unit. So for today, what I really want you to take away from this lecture is, how do we determine the net ionic equations? Now, one last thing. There are 7 strong acids. There are 7 acids that completely dissociate into its ions. I've given you those 7. So when you do this homework for today, please consult or write these ions down, as you have them on a piece of paper next to you. On the test, I will give you all of these acids so you have them in front of you. These are the acids that completely dissociate into ions. If you have a substance that begins with an H, it is an acid. If it's not one of the 7 strong acids, then it will not dissociate. And I'll show you examples of that with these net ionic equations. Okay, so if it begins with H, it's an acid. Then you have to look up, is it a strong acid or is it weak, and you'll see what the difference is when I do the homework problems. Okay, so strong acids completely separate. Same thing for the strong bases. Strong bases also completely separate. What are the strong bases? They are typically the hydroxides of group 1 and group 2. So if you look at the periodic table, group 1, sodium, potassium, rubidium, cesium. Group 2, calcium, strontium, barium. Any of the group 1 and group 2 metal ions put with hydroxides are the strong bases. A weak base, only a little bit of it separates. Strong bases completely separate. So again, that's the difference between strong and weak. Does it separate? Does it not? And we'll see now with the net ionic equations. Okay, so let's put this into example. This is what primarily your homework will be off of. And hopefully by seeing a couple examples, the homework will make sense. It'll be a lot easier for you. If not, again, I will be available to talk on Thursday at 1 p.m. Chime in and we can talk about what you're struggling with these net ionic equations. Okay? All right, so strong acid with a strong base. There are 3 combinations now that we can have that are testable in the AP chemistry exam that'll also be put on this test. The most common that you're going to see on the test is a strong acid with a strong base. So write the net ionic equation for the reaction between HCl and sodium hydroxide. All right, let's first do the molecular equation. So I'm going to write down all acids and bases are aqueous. Okay, so the substance that begin with the H is the acid. The substance that ends in OH is going to be a base. So the HCl is going to donate a proton to NaOH, and that's going to form H2O. Now, what state is water? It is not aqueous. Aqueous is something dissolved in water. Water, all these reactions take place at room temperature, so water will always be a liquid. Okay? So the HCl donates the proton. So the H plus of the acid goes with the OH of the base, OH minus of the base, producing water, H2O. The sodium ion then goes with the chloride ion, forming sodium chloride. Now, as I said, this is a salt, and now we have to look up our solubility rules like we did for the last examples, and you'll notice that, or you should already know, sodium chloride is normal table salt. Table salt is soluble in water. Since water is always present in these reactions, they're always aqueous solutions, and we also produce water as one of the products, almost all of the salts that we're going to form are going to be soluble. Actually, I believe I'm not going to trick you at all. The salt that's always formed is going to be aqueous. All right? And if you look at the reaction, it's perfectly balanced. There's the molecular equation. Okay? So acid plus base produces water and salt. Okay? Now, the complete ionic equation. Now, here is where things are a little bit different. In the last example, anything that was aqueous, we would immediately break it apart into its ions to make the complete ionic equation. That's true for most of these compounds, except now for the acid and the base. We are not going to ask the question, is it soluble? We already know that. Do we break it apart? Is instead the question to be asked is it strong or weak? If it is strong, we are going to break it apart into its ions, because a strong acid and base completely ionize, separate into its ions. Weak ones do not. But because this is an example of a strong acid with a strong base, we know that both acid and base are strong, so they will separate. So the HCl will separate completely into H plus and Cl minus. The sodium hydroxide will break apart into sodium ions and hydroxide ions. Now, I know what you're going to say. What about this idea of hydronium ions up above? The H plus, the protons that are given up by the HCl typically do not stay in solution. Why? There's millions and millions of water molecules. So like I showed up here, any protons that are given up by the HCl will quickly jump on a water molecule forming the hydronium ion. So a hydronium ion is synonymous with an H plus particle. Okay, so I'm just going to write as H plus to simplify things, and I would recommend you do the same thing for yourself. Just understand that you wouldn't see it in water because it would be attached to a water molecule to stabilize it. All right, water side. Water is a liquid. Because it is a liquid, anything that's a liquid, gas, or solid, in any of these reactions, we leave alone. We do not separate them. Sodium chloride is a soluble ionic salt, like the last lecture. We will immediately separate it into its ions, and right there is the complete ionic equation. Next step is exactly the same as the last homework. Are there any spectator ions? Are there any ions that have done nothing chemically? Are they the same on the left side as the right side? And you should say yes. The sodium ions are spectator ions. They do nothing chemically. There were sodium ions before we mixed, and now they're still there after we mixed. Same thing for the chloride ions. So the spectator ions, you would say, would be the, would be the sodium ions and the chloride ions. What's left is the net ionic equation. The great thing is if you can answer the first key question, when you identify that it's an acid-base reaction, it begins with H, it ends in OH. If you then ask the second question, are they strong or weak? If you can identify that the acid is strong, and you'll know that because I'm going to give you the 7 strong acids as a list on the test. It'll be part of the instructions. If it is a base containing a group 1 or group 2 metal, okay? Group 1, group 2 on the periodic table, it is a strong. If you identify that it's a strong acid and a strong base, it's as simple as this. Any strong acid with any strong base, doesn't matter which it is. Any of these combinations up here, any strong acid mixed with any of the strong bases, immediately the net ionic equation is H plus OH minus produces H2O. Always. So it literally becomes, you immediately know the net ionic equation. You don't even have to go through all of this work. If the question is, what is the net ionic equation of this acid and base? If they are both strong, acid and base, you will immediately will get this net ionic equation. Okay? Now, what's the misconception? Students will immediately always say that this is the net ionic equation for all acid and base reactions. It is only the net ionic equation when we mix a strong acid with a strong base. Okay, so let's look at a couple examples where it's not a strong with a strong. So here's an example of a weak acid with a strong base. How do I know that? HF, if I look up HF on my 7 strong acid table, it's not on there. If it's not one of the 7 strong, we immediately know that it's a weak acid. KOH is a hydroxide. It contains OH. It's a base. And I know it's a strong base because potassium is in group 1. Since the metal is in group 1, I know it's a strong base. So this is an example of a weak acid with a strong base. Okay, so let's write the molecular equation. HF. Again, all acids are aqueous. All bases are aqueous. That doesn't tell us if we break them apart or not. Okay, again, the acid, regardless if it's weak or strong, the acid is going to donate a proton to the base, producing water. We will always get water for all of these reactions. The acid donates a proton to the base. The potassium, the positive part of the base, goes with the negative part of the acid, producing a salt. In this case, the salt is potassium fluoride, and potassium fluoride is readily soluble in water, so it's aqueous. All right. Again, the reaction is perfectly balanced. Everything's +1, -1, so that's going to be pretty simple. It's not always the case, which you'll see with the homework. Sometimes the ions have got a +2 or -2 charge, and you got to be careful with balancing. But again, I will show you the answers to these, so if you have any questions, just ask. All right, now, to break them apart, the acid and base, to break them apart, we don't immediately break them apart because we see the aqueous. We break them apart as if they're strong. Now, we said HF is a weak acid. If it's a weak acid, what we do not do now, this is the only time we do not separate something that's labeled as an AQ. The HF we keep together because only a small amount of it will actually break apart. Okay? Therefore, almost all of it stays together as its molecular form. It stays together as HF. The potassium hydroxide, however, is a strong base. Because it is strong, we immediately separate it. And again, whenever it breaks apart into ions, we no longer have to label it with an AQ, because if it's an ion, we know that it's aqueous. Do I break the water apart? No, because it's labeled with an L. Do I break the potassium fluoride apart? Any ionic compound. Now potassium fluoride is not an acid or a base, it's a salt. The second compound is always a salt. If it's a salt, we break it apart if it's immediately labeled in aqueous, just like yesterday's homework. All right, so the potassium and the fluoride will break apart into its ions. All right, are there any spectator ions? Are there any ions that have not changed at all? They're the same before the arrow and after the arrow. There's only one now, the potassium. The potassium ions is the spectator ions. I think it's exactly the same both sides of the arrow. What I'm left with is the net ionic equation. Now, yesterday when we talked about balancing the reaction, remember it has to be balanced in two things. Do you remember what those two things are? The first thing we have to look at is it balanced in atoms? Okay, let's take a look. There are two H's on the left. There are two H's on the right. There's an oxygen on the left. There's an oxygen on the right. There's a fluorine on the left. There's a fluorine on the right. The atoms are balanced perfectly. What's the second thing we have to be careful with that we are balanced in charge? Is it balanced in? My bad, I gave it away. Is it balanced in charge? Okay. Well, if I look at the left side, is there any charges? The HF has no charge, but the OH has a -1. So it's got a charge of -1 on the left. Do I have -1 on the right? 0 for the water, but there's a minus on the F, so -1. So yes, we are equal. We are equal in both atoms and charge. So this is the net ionic equation for a weak acid with a strong base. So whenever we have a weak acid with a strong base, what we are going to get is the formula of the weak acid is going to be exactly as it is given. We're not going to break it apart. The strong base, the positive part of the strong base will be the spectator ion. So all we are left with was the hydroxide ion. That's going to produce water and the negative ion of the acid. That is the generic equation for all weak acid, strong base reactions. And that's what your homework is going to be on. Your homework is only going to be strong acids with strong bases and weak acid with strong bases, because these are the two most common types of acid-base reactions that we have. Okay? I am going to show the third here, but it is not going to be on the test. It's not going to be in the homework. But for those of you that want that extension, I'm going to do it now. If you want to just stop the lecture and then that's all you have to do for Wednesday, and then Thursday do the homework problems, you can gladly do that. But I'm just going to show you the last type of reaction that is on the AP Chemistry exam, especially for those of you that are planning on taking AP Chemistry next year. Okay? Otherwise, thanks for listening. All right, for those of you that are planning to stick through, the last type of reaction is a strong acid with a weak base. So here we have nitric acid, which is a strong acid. The most common weak base on the national exam is ammonia. Ammonia is a weak base. All right. And the weak base, most of the weak bases contain nitrogen and hydrogen, either amine or amide compounds. These are a lot of organic compounds, but anything containing nitrogen often is a weak base. Okay? So, just like before, what do acids do to bases? Acids donate a proton. So therefore, NH3 is going to become NH4, the ammonium ion. And because it's a charged particle, I don't have to put aqueous after it. If you did, no big deal, but you don't have to. What's left with the acid, the strong acid? NO3 minus. Okay? And that's it. In a strong acid with a weak base, the strong acid donates the proton to the weak base, and that is the reaction. What we don't see produced is actually the water molecule. It's there. Water's present because we have aqueous solutions, but it's not part of the overall molecular equation, which makes it odd, and that's partly why I said if you didn't want to look at this example, you wouldn't have to, because I want to confuse some of the students that might not want to worry about that. Okay? The complete ionic equation now. Do I separate the nitric acid? Yes. Why? Because it's a strong acid. I would not separate nitric acid if it's a weak acid. Do I separate ammonia? No, because it's a weak base. So just like weak acids, weak bases we leave together. Okay? The other side, because they're already ions, there's nothing else left to do. They've already actually been dissociated for us. So we just leave them together. All right, that right there would be the complete ionic equation. We would only need to separate the strong acid or the strong bases. In this case, we only have a strong acid. It's separated. Okay, are there any spectator ions? You'll notice that the nitrate is the same on both sides. We cross it off, and what we're left with is the net ionic equation. So this is a very odd one in the fact that we don't get the production of water. And that's probably why I didn't want to show it to all students. But this is the generic equation for a weak base with a strong acid. With a weak base and a strong acid, we would write the formula of the weak base, the strong acid, the negative part of the acid, the nitrate, the chloride, the bromide. The negative part of the acid would be a spectator ion. It is no longer part of the net ionic equation. All we get with the strong acid is the proton. So literally the strong acid, the proton of the strong acid combines with the weak base, forming the ion. Okay? And this ion is actually called something called the conjugate acid, which I'm not going to get into now, but we'll talk more about this when we get into the acid-base chemistry unit. So right there is the generic equation for a weak base and a strong acid. Okay? So the weak base will get a proton added to it from the strong acid, forming a molecule we just added together. Actually, not really molecule, an ion, because it's going to have a charge on it. All right, so again, I appreciate you listening to this. The homework is going to, again, only be off of strong acid, strong bases, or weak acid, strong base problems. And I'll get those answer keys up online sometime today, which today is Tuesday. I'll get those up online within the next hour or so. So if you do decide to start the homework today, the answer keys will be provided for you. Again, thanks for listening. And again, Thursday, if you have any questions on this stuff, I'll be available at 1 o'clock. If you go to that link on Canvas and have uploaded Microsoft Teams to your iPad, you can chime in with any questions you might have on this net ionic equation stuff. And then Friday will be the quiz. The quiz will be on concentration, calculating concentrations, and also some of these net ionic equations. All right. Thanks a lot for listening.